Now we're going to turn to the axial capacity of driven piles. And to lead off my discussion, I'm going to go back to something that took place 31 years ago. In 1989, Professor Richard Fenno at Northwestern hosted a conference on the axial capacity of piles, and to take into account lots of effects, and most of those we're going to discuss today. And he drove some H-beams and pipe piles, and he did all kinds of measurements, some dynamic measurements, some static measurements. We're going to talk about all of that too. But he invited a group of academics to predict in advance what they thought the axial capacity of the pile would be. And the academics from a broad range of a very wide range of those who were active in the industry at the time. And they employed no fewer than 24 methods to determine the axial capacity. And that's just the axial capacity. It doesn't get into the issues of how do I predict pour setup and all the other stuff. So he did that, and he got a fairly broad range of answers. Now, it was risky for the academics because, as you've probably learned by now, academics don't like to be wrong. And the only thing they like less than being wrong is being shown that they are wrong. So this was not a good thing, but they had the temerity to stick their necks out and to let the chips fall where they may. And like I said, they got a wide variety of answers to this question. I've mentioned before that geotechnical engineering has a bad habit of multiplying its methodologies. And nowhere that I know of where is that become more apparent than it is here with driven pile capacity. And there are many problems associated with driven pile capacity that you don't see in virtually any other place in geotech. You have issues such as cavity expansion. Cavity expansion is the phenomenon where, say if you drive a nail into a piece of wood, the wood is going to have to expand, or the wood's going to have to get out of the way, so to speak, so that the nail can go in. The nail takes up a certain amount of volume. In the process of being driven into the wood, the nail actually compresses the wood around it. And that compression, that radial compression, becomes axial compression, and that basically helps hold the nail in place through friction along the surface of the nail. You get the same thing with driven piles. The problem is that some driven piles are either displacement, where they have like a square concrete pile, or a closed-in pipe pile where they displace quite a lot of soil. And I know these are very vague terms, and unfortunately the way we've handled them isn't very helpful. And then there's non-displacement piles like H-beams, and if you use them for axial capacity sheeting. And as a result, they don't displace the same way, and you don't get the same results. Your materials, anybody who's driven, who's been involved in pile driving knows that steel, concrete, and wood don't drive, quote unquote, the same. They have different densities, acoustic speeds, flexibility, all kinds of stuff. That means that they drive differently, they have different effects of the hammer, they have to be handled differently, either during setup, setting the pile into place, and during driving. So there's a lot of non-uniformity in that. You also have the fact that when you get into pile dynamics, that the resistance of a pile during driving, the dynamic resistance of soils, and the static resistance of soils aren't always the same. obviously you have effects due to the velocity, but you also have different strain rate effects in the soil. So it's not surprising really that we have the condition we have, and that's why we have so many methods. And you're going to see there's another listing of methods, not quite this many in your book, that goes over the same issue. So it's a situation where the science is not settled, but probably the biggest trout in the milk in the whole thing is the fact that the whole premise of bearing capacity in piles is not really realistic. So let's go ahead and get started with that. The basic bottom line, except in very rare cases where you've got some very soft soils, very high loads, or whatever, catastrophic limit state failure of deep foundations, and this is true both with driven piles and drill shafts, is rare due to the difficulties in generating a clean failure surface. And this has been argued principally around the pile toe, the end of the pile. And it has people have tried to model the pile toe in the same way that they model shallow foundations, and it just doesn't work. There's too much overburden above it. There are too many other factors. There's the issue of how the pile and the soil interact on the way down, and that all of these contribute to the simple fact that bearing capacity at the toe is a term we can only use very loosely. We can't really get down to get really specific. It's something we have to use with a asterisk next to it, basically. As I said, though, we've in spite of the fact, the shaft failure is completely different. It's a combination of a frictional failure and also involves to some extent the elasticity of the soil. The settlement of a pile also involves the elasticity of the pile. We're going to get into this when we get to settlement. But in spite of the fact that the theoretical basis of bearing capacity is iffy, that hasn't stopped us from developing an extensive collection of methods. Some of that is due to the fact that in times past, the computational power most engineers had available to them to design projects was limited. So a simple formula was useful, and it's still useful in some applications if we understand their limitations. So therefore, we traditionally do not blindly design deep foundations by these static methods. Certainly not driven piles and to drill shafts to a little bit, not much. We use these as guides to get us started. And I think you need to keep that in mind as you move forward. The basic bottom line for driven piles, and also for drill shafts as well, is they fail through excessive settlement. And bearing capacity, pure straight up bearing capacity failure is very rare. And that's the normal way we would expect it. And we would, the best way to anticipate that settlement is to model the pile according to using a model which includes the flexibility of the pile, the flexibility of the soil, and the plasticity of the soil, and a progressively applied load. And those are called TZ methods, and those are very there's software today that will actually estimate those. It's just that it's many of our design methodology doesn't allow us. It's depending on the agency or whoever you're working for, doesn't allow people to actually use those as the definitive way of designing a pile. The methodology we have is based upon something I discussed earlier, which is we design for strength and we design for service. And with driven piles, really the two run together. But because of our design methodology, we have set things up so that we have design for strength and design for are basically designed separately. But keep in mind, as you use these methods, that they're certainly related and they really cannot be separated one from the other. So if you understand that going in, I think design of deep foundations becomes a little simpler. We call the methods bearing capacity analysis, but really settlement is ultimately what we're going for. But we're going to start with bearing capacity. Again, it's codified in the codes. It's codified in AASHTO's design method. So we need to at least understand it, even if we understand that that method has serious limitations to it. But in any case, no matter whether you use this method based on bearing capacity, quote unquote, settlement, or both, any method needs to be verified either by static testing, dynamic testing in the field, or preferably both. And this is true of certainly of driven piles, and to a lesser extent drill shafts. Drill shafts are sometimes difficult to statically test. And drill shafts have some other issues as well. We're going to get into that. Now, this is a topic which for some reason has buffaloed my students for a long time. And I'm not really sure why. And that is the shaft resistance and the toe resistance. So maybe I should start with some definitions. And I'm going to use something which maybe some of you will understand. This fine object, which is emblazoned with my prep school's logo on it, which should give you an idea what kind of prep school I went to. And the impression would not be wrong either. Has a, let's say this is a pile or even a drill shaft. It doesn't matter if it's pile, drill shaft, whatever. It has the shaft is the area along the side of this thing. All here. All this area is the shaft area. And the toe area is this, what's on the end. And if I were to sink this into the ground and put a load on it, the load would be distributed between the friction against it along the shaft and the friction against it at the bearing resistance at the toe. And that, the two of them, is how we get axial capacity in piles. Now, it is important to understand that concept. Now, also important to understand is the fact that as I load this is going to go further down. And basically, and this is going to have axial flexibility. And that's hard to see with this, but it does. It has axial flexibility. And basically, these are resisting springs with a limiting resistance. In other words, they're elastoplastic. And as I go down further, the soil at the top, say I've immersed it up to here, to this rim, the soil at the top will basically go plastic first. And as I further push on this thing, the elastic will go down, and eventually you will have all the shaft resistance. If I put enough load on it, the shaft will eventually load up completely, will eventually be all plastic. At this point, I say that I've completely mobilized the shaft resistance. Now, for someone who designed impact pile driving equipment, it took me a while to really get with this concept. Because when I think of something moving, I'm thinking of something flying down at 13 feet per second and making impact. This is not my idea. Was not my idea of moving, but that's civils. That's about as good as it gets. So, and then once I completely mobilize it, the toe is likewise got an elastoplastic, and eventually, if I keep going it, I will eventually hit the plastic limit on the toe. Now, that's a little more problematic because you've got a lot of sole under it, and it's a little more complicated, but eventually when I hit that, I say that I've mobilized the shaft resistance, the toe, I've mobilized all of it. And I guess you would call that a bearing capacity failure somewhat. So that's, in a nutshell, is the shaft and the toe. Now, this is another place where students get buffaloed. I talk about the shaft area and the toe area. Okay. Let me describe both of you using the same object. The shaft area is basically the surface area of this jug that I'm holding in my hand, right here, or hands, right here. It can be computed by basically, it's round. And in this particular case, you have basically the perimeter is pi times the diameter of this thing. And therefore the surface area is pi times the diameter of it times the length of it. In other words, the distance from here to here. That's the shaft area of this thing. If I have, say, a layer change halfway through, and whatever unit resistance I have changes for some reason, and we'll talk about the reasons it changes in just a minute, then from here halfway down, for example, is this length times this is the shaft area for this layer, and this length times this diameter, this perimeter, is the shaft area down here. That's how you compute shaft area. Toe area, on the other hand, is just the end of this thing. And basically, in this case, it's pi d squared over 4 for a closed end. If this end were open, it would simply be the rim, taking into account plugging issues, which we'll get into later. And so the rim of this thing is, if it were open, it would be just the rim. If it's not, it's the whole area, like a closed-end pipe pile. That, in a nutshell, is how you compute your shaft areas and your toe areas and what shaft resistance and toe resistance is. So that's my way of illustrating it. The total resistance of a pile is equal to its total shaft resistance, which is a force, plus the total toe resistance or point resistance, which is also a force. And right off the bat, the problems with the resistance is that now, that's the ultimate axial capacity is equal to the resistance of the total possible resistance of the shaft when the sole is fully mobilized, plus the resistance of the toe when it's fully mobilized. Now, I talked about mobilization just a minute ago. You do not obviously want, except in static load testing maybe, and a lot of times not even then, want to load to its ultimate, a pile to its ultimate, unless you're doing it like some acceptance, maybe static load testing. We're going to see in load testing that it's more complicated, but basically that's the concept. The shaft resistance, as I point out, is, now I know when you see the integral sign, fear strikes in the heart, but like I tell people all the time, one of the reasons why people go into geotech is because their math's not the greatest. And I kind of made that half as a joke, but we don't normally, unless you're doing very theoretical work, we normally don't do integrate. What we do is piecewise. We say that, as I said, you remember I had this up here, and I had this part of the shaft and this part of the shaft. And say if this is split in half, this part of the shaft has a unit shaft resistance. Pounds per square foot, kips per square foot, kilonewtons per square meter times square meters or square feet give you force. That's what this term is all about. Now you ask, how do I compute Fs? Well, that's the fun part. That's where we get into the 24 different methods. The toe area, on the other hand, is equal to the ultimate toe resistance times the this area, as I discussed. The toe, and that toe again is in force per unit area, pressure, stress, whatever you want to call it, against here, times AT. And we're going to talk about how to compute QT. AT well, we'll talk about that. So that, in a nutshell, is how you do. And drill shafts are no different. The big advantage of drill shafts is they're all around. Same with auger cast piles. Well, let's put it, the drill shafts are supposed to be around. We'll see in a minute. We'll see when we get there that one of the objectives of any drill shaft contractor is to make sure that their drill shafts are in fact round to a reasonable degree. Load transfer characteristics. Unlike shallow foundations, deep foundations transfer the load. Actually, shallow foundations do. It's just that our theory doesn't really take into account. The other thing is the progress is a little bit faster with shallow foundations. No, it's a lot faster with shallow foundations. I'll take that back. And it's due to the flexibility of the pile and variations in the soil resistance. There are different kinds of way of distributing the shaft resistance and splitting resistance between shaft and toe, depending upon the type of thing. For example, you have the first one is a toe bearing pile, and you see that. In fact, many of the piles driven in this area are basically designed as toe bearing piles. You drive H-beam to rock, declare victory, and move on to the next one. So therefore, the shaft is a uniform, basically acts as an axial member, and it transfers load from up here down here to the rock, and then we're done. If you have, for example, a typical cohesive soil, and we're going to talk about how this is an oversimplification, then you can, if they're in theory, and I don't think it really works out in some theory, let's put it that way. If cohesion is uniform then along the shaft, then the Fs, little fs, is uniform along the shaft, and you get this. With cohesionless soils, it's dependent upon the effective stress, so you forget your classic triangle variation. I'm going to show that the last case is really can be used to design any driven piles. Now with drill shafts, it's a different story. And I'm going to explain why that in just a minute. We have driven pile factors of safety. Factor of safety is pretty much a factor of safety. And these are typical factors of safety which we use. LRFD has altered this, and we'll get into that when we get to LRFD. But for the moment, let's just design using ASD and the factors of safety. Okay, using a static method. Now, your book has a nice explanation, and I'm not going to go through blow by blow and repeat it, of how we do that. This particular one, this is figure 9-5. And we have basically we have, as you see, we've got 3 layers of soil, and then we have this pile. It has we want to know the ultimate capacity of it. So, for purposes of, and I'm just going to summarize this because the book goes through a pretty decent explanation, and the example that follows is likewise an explanation. And we'll just go on to that. You've got 3 layers here. The first layer, if you recall, I'm going to go back, is a subject to scour. A layer that is subject to scour is kind of like the team member on a group that really doesn't want to contribute. When you really need this person to come through you, they don't show up. And that's what it is, that's the way it is with scour. And so we're going to talk about, so basically for axial capacity purposes, we eliminate. We don't even consider the scour layer. The second is a soft clay, and now the soft clay may have some down drag issues, and we're going to mention those later, but for the moment we're going to say the soft clay is not going to help us either. It's not very good. The last layer is a gravel layer, and the gravel layer, we're going to assume that for both the purposes of shaft and toe, the gravel layer is the deal. And so therefore, all we do to get the ultimate axial capacity of this, bearing capacity of this pile, is we add the shaft resistance in the gravel and the shaft and the toe resistance in the gravel, and we're done. And that's what this example is all about. For drivability studies, it's different. We have to drive through all 3 layers, because all 3 layers are there for one thing, and therefore we consider all 3 layers in the drivability studies. Therefore, the what we call SRD, which is soil resistance due to driving, is different from the ultimate capacity. They don't necessarily have to be the same. In most decent stratigraphies they are, but there are some like this one where they're not. So we have a different value for each. You have to be careful about that when you're designing driven piles. So this is a nice example that shows you how, one thing you'll notice in the driving capacity is, or the SRD, is the nice term that we use now for it. I don't know if your book uses it or not, but that's what we do now. Is the driving capacity has a sensitivity. And I'm going to talk about sensitivity and setup later. Now we have methods for static analysis. And you see that the book admits, this comes from the Driven Pile Manual. Your book doesn't really admit this, but the Driven Pile Manual, which this is the newest Driven Pile, there have been, I think, 4. I think this is the 4th edition of the Driven Pile Manual FHWA's put out. There are a lot of methods. You see here, and this just scratches the surface of them. The method your book, I need to explain why I picked the method I have. Your book presents 2 different methods, and I'm going to explain why the method I picked is justified. But anyway, you see we've got a multiplicity of methods. Some people, when they're teaching this subject, want to go into, well, your book does at least 2, and there are other, and it used to do some other ones. The earlier versions of the Soils and Foundations Reference Manual had n-value methods, and I'm not sure if the CPT method is still in there or not, but I know they had this SPT method, Meyerhoff's SPT methods and whatnot. And I've tried to teach those over the years with varying degrees of success. So we're going to stick with, my approach to this is I'm going to teach you one method. I'm going to explain why I don't use the other one. And we're going to focus our attention. Some foundations courses will teach you 2 or 3 methods. Which method, and the problem is that if you teach method A and you go out and work for somebody, they'll say, well, no, we don't use that. We use method C or D or whatever. And then you'll have to use it. And then unless you can come up with a justification, well, no, there's a better way to do this. And there's the methods that are being developed. And the method you use in the TAMWAVE program is different altogether from the methods that we're going to show you here. Method we're going to talk about is the Frillenius method. There are 2 methods in your book. One of them is actually 2 methods rolled into one. It's Nordland-Tomlinson method. They're not really the same method. The Nordland method is for sands, and the Tomlinson method is for clays. And it's based upon a concept which I think is subject to revision. And I'm going to explain why. Particularly Tomlinson's method I think needs a good overhaul. There are 2, basically for shaft resistance particularly, there are 2 methods that we use which are called alpha methods and beta methods. Alpha methods is like Tomlinson's, and your book describes this in detail, we use with clays. And basically it works under the classic Moore-Coulomb assumption that the strength of the soil in pure cohesive conditions is related to, at least, or proportional to use the proper term, the undrained shear strength or cohesion. And that is equal in turn as times, and the proportionality constant is called alpha. Thus they're called alpha methods. On the other hand, you have in sands, you have a situation where as like with any other cohesion of the soil, it does not develop the strength unless it is being compressed by the effective stress. And the effective stress this way produces strength, pressure this way, and that pressure acts against the shaft of the pile, and therefore the soil strength is affected by the effective stress, and the frictional resistance is by the effective stress. And it's basically equal to beta times the effective stress. Thus they're called beta methods, and we can break that down further. That was pretty much very much of an accepted way of doing things, and that's the FHWA's rationale with the Nordland/Tomlinson. The Tomlinson is your classic alpha method, and your Nordland is a beta method. And until the early 1970s, nobody really challenged it. It was John Berlin, who is a British geotechnical researcher and one of the best, observed that due to remolding, cohesive soils basically, and we see this with retaining walls, and I talked about this with retaining walls, basically, and if you can't get any kind of remolding during impact pile driving, you can't get it. But he basically stated that these soils remold to the point where they act more like cohesionless soils, which means they have a phi. And therefore, that all soils basically should, and all these things should basically be analyzed by a beta method. The result of this was controversy. But in the intervening years, what we have discovered is that he was basically right. That, and with cohesionless soils, there's no question about it. With cohesive soils, the relationship between Cu and there is a relationship between Cu and effective stress, which basically means that we still need to know the effective stress even in cohesive layers. And depending on how we do the math, and I've got some stuff on my website which discusses this issue, we can either set them up as alpha methods or beta methods. Either way. It seems to me a lot easier way to set them up as a beta method, the whole thing. In other words, if you compute the effective stress, why not just use a beta method? And that's basically Bengt Fellenius' idea behind his method. Basically, all of the little FS's and the QT's at the toe are based upon, well, in this case, he's got the FS, which is beta times the P naught, or the effective stress. The effective stress for any layer is taken at its center. Obviously, the more layers, if you divide up into more layers, you get more effective stresses. You might get a little bit better profile of what's going on. But irrespective of how you divide it, that's little fs for that particular layer. You take it in the middle, just like you did when we were working with cohesive soils and consolidation. Remember the middle of the layer thing? Well, guess what? It's come back to haunt us. And we're back again. And the effective and the QT at the toe is equal to the effective stress at the toe times some bearing capacity factor. Now, just because we say that, well, we don't like the idea of bearing capacity at the toe as a concept, doesn't mean we can't find it useful as a computational aid. It depends a lot on how you formulate the bearing capacity factor. Fellenius, basically, there are two ways the book shows how to do it. One of them is this table 9-7, which for given soil types, you have different ranges of beta factors and ranges of bearing capacity factors at the toe. You can use that to determine your little FS's and your little QT's. Or you've also got these charts as well. Once you've done that for each layer, then you add them all up. And actually, you use either one. Just make sure that you understand that you clearly indicate the source of where it's coming from. You should always do that with any type of calculation like that. In fact, that's good practice for your geotechnical reports to say, well, this method comes from this particular reference. You should always reference the method that you do. Otherwise, you're subject to challenge. Well, where'd you come up with this? And then if you can't explain it, then say, well, this is no good. So as a matter of, students, we talk about references and citing references as a matter of plagiarism, of defense against plagiarism, where it's, well, this comes from here. But it's also in practice a matter of basic, this is the method I use. It is an accepted method. It doesn't necessarily mean it's right, but it's an accepted method. It'll come a lot closer to being right if it has some type of acceptance. I'm not saying that that's an absolute guarantee. And I'm not saying that just because the methods have problems. They do. But that's just geotech. The other thing, of course, is that there's always that certain soil that screws up all of our presuppositions. So we have to be aware of that. I think the Fellenius method, personally, is for general application the best one. The example in your book, I don't know where they got it from. It has nothing to do with the Fellenius method. Nothing. So we're going to construct a different example from a different source. And I'm going to show you how to do the Fellenius method. Let's consider this example. It involves a layer of 5 feet of this soft soil, which we're going to assume to be clay. Why do I assume it to be clay? Well, generally speaking, if it's considered a soft soil, it's clay. And below that is a dense sand. Now, this is the way that this problem is stated is a little tricky. And I'm going to explain how. First of all, you'll notice that the soft wall has a total unit weight of 80 PCF, 80 pounds per cubic foot. But you'll also notice that there's gamma B. What is gamma B? Gamma B is the buoyant weight, or what we normally prefer to call in this course the submerged unit weight of the salt. So if we were writing, I got this from DM7, if we were writing this out, I would say it's gamma prime. It is one thing you must be prepared for, and we saw some of this in soil mechanics, is that when you have layers and you're given unit weights, and be thankful you're given unit weights because a lot of boring logs don't have them, that frequently the gamma will be given to you in submerged unit weight, not necessarily in total unit weight, and then you subtract the U from it. So be careful. The dense sand has a gamma B of 65, or a submerged unit. And that, if you double that, that's about 130 PCF, which is about what you expect with a dense sand, but it's buoyant. One of the advantages of getting buoyant weights is it eliminates all the poor water pressure calculations and makes your effective stress a lot easier. The only trout in the milk in this thing is down here at the bottom. You'll notice they have this thing where it flattens out. That is due to the method they use in DM7 is different from this one, and it assumes many of your driven pile methods assume that the FS only goes up to a certain amount and then quits. There's no real scientific basis for that. There are other reasons why sometimes the FS at the toe is lower, but to model that you have to get into the same kind of methods I used with TamWave. And I'm not going to go into that. But anyway, let's just, to keep things simple, let's just assume that let's just use this effective stress profile the way they've given it to us. If we didn't, what we would do is just keep going here until it hits somewhere out here. But just to keep life simple, let's just use what they've given us. It's basically a 4-layer system. We're going to drive a 12-inch close-in pipe pile as shown. We want the ultimate and allowable capacities. Okay. All right, we've got okay. There are 4 layers, 2 in the soft clay and 2 in the dense sand. This is a beta method. We compute the effective stress in all the layers. In this case, we don't have to construct a P0, it's given to us. We're just going to use theirs, just for fun, just to make it simple. Layer 1. Now, this is your basic, this is how you compute in the center layer. If you've got the effective stress at the top of the layer and the bottom of the layer, the center layer is the average of the two. And that's the way we compute them all, except for the last one. And by the way, they should be layer 1, 2, 3, and 4, rather than just layer 1, 2, 3, and 4. So the 4 layers, you just average the effective stress top and bottom, and you're done. I'm just going to use 1 layer for the very thick, for the thick portion of the dense sand. That's it. The first thing we need to do, now we've got all the effective stresses figured out, is to compute the Falanis' beta. For the top 2 layers, we're going to assume that beta is 0.15, which I got from table 9-7. For the bottom 2 layers, we're going to assume beta is equal to 0.3, which I got from figure 9.17. Again, it's important to reference where it comes from. And all I do, once I get that, it's pretty simple. One thing that Bengt is very insistent on with his method is that he insists that the beta factors you actually use should be based upon experience. I agree with him wholeheartedly on that. Obviously, when you're learning it, you're kind of going to take your half out of the middle or guess or whatever. But in practice, you should be able to have, based on experience and whatnot, should be able to compute what your beta factors need to be. But shaft layer unit resistances, layer 1, all I do is take the top beta and multiply it by the effective stress for layer 1, and I get 0.012 KSF. Yeah, I'm not real fond of the KSF. PSF would result in 12 PSF, but we're just going to stick with it. Just keep our units consistent. Layer 2, the same thing. Layer 3, I switch to the sand, which is 0.3, and I multiply that. And layer 4, I multiply it by that effective stress, and I get this. I have 4 little F1, F2, F3, and F4. And that's how I get my friction factors. That's the beauty of the Fellenius method. It's simple. It does require a lot of judgment, but face it, in this business, they all require a lot of judgment. You always have to develop that as you go along. Now we need to compute the shaft resistance for each layer. I have to have the the areas. Now, how did I get the layer areas? Well, what I did was this. It's just like, let's see, we have the shaft layer areas. I think I skipped a slide in there, but I'm back to this. I have to do the areas. The perimeter, it's a uniform pile, so the perimeter is 3.1416 feet. Layer 1 is 2 feet 6, so I multiply that by 2 feet. Layer 2 is A2, I multiply it by 3 feet. Layer 3 is A3, multiply it by that. Layer 4 is that, multiply it by that. That's all. That's all there is to it. I get those. You just follow along. Now, most of the piles in this course will have a uniform cross-section, which means that they'll have a uniform perimeter all the way down. In some cases, you get tapered piles, you get piles of 2 different kinds, composite piles. This may not be true, so be careful. Now we go through that. I just take those little F's and the areas and multiply them together. In this way, layer 1, layer 2, layer 3, layer 4. That's all I do. And then I get a total shaft resistance, and just add all those up at 24.3 kips. That's ultimate. Toe resistance, well, there's only one toe. Now, sometimes I will see students when they're solving these problems give me a toe resistance for every layer. No. Unless you're doing stuff like drivability studies, where you progressively, you're progressively moving, going, where you need to have a progressive, your pile resistance progressively increases as you go in the ground. You don't really need to do that. Just one toe resistance, and if you're doing a full penetration of the pile. The sand layer, the effective stress of the toe is 1.535 KSF. The value of N sub T at the toe is 25. And then all I have to do is around 20. Yeah, around 25. Figure 9-18, since the pile is closed-ended, the area is the cross-sectional area of a circle. Closed-ended, 0.785 square feet. The toe resistance QT is just simply equal to the N sub T times the effective stress times the area. It gets 30.1 kips. So most of this pile resistance is at the toe. I multiply up, add 2 together, I get 54.1 kips. Total ultimate resistance is 54.1 kips. We call for static load testing. Fs is equal to 2. And I simply divide that by the factor of safety. You see the table below, which I've shown you before. I end up with an allowable capacity of 27.05 kips. Now we get into what I guess is best considered the ifs, ands, and the buts sections of this topic. Up to now, I've given you an overview of the whole idea of profile and contact areas in their simplest form. By the way, just as an aside, if you have a computer that will handle the old, and I have a whole web piece on the whole issue of why a lot of older Windows software doesn't work anymore. If you have a computer that will handle it, and I'll also explain how one can be had, then I would strongly, the FHWA put out a program which could be downloaded from my site called Driven. And Driven uses the Nordland and Tomlinson methods you have in your book. And you can see how the software implementations would work. Since Driven was the issue, I believe you've got commercialization of that. The problem with commercialization of anything, of course, is it's expensive. So that's why I don't. And with Driven, one time I could actually get my students to use Driven, but I don't think, particularly the way that Windows has gone, I don't think I can do that anymore. So, with that in mind, we're going to talk about, and it's not a bad idea to learn how to do it the hard way anyway. So, with that, we'll talk about contact areas. We have two basic types of section foundations, closed sections and open sections. Closed sections where the soil foundation soil contact takes place along a well-defined border between the pile and the soil. Most piles, and that includes your concrete piles, unless you get into your cylinder piles to some extent, your closed-in pipe piles, obviously, and wood piles are all in that category. Open section foundations is sometimes where the contact area is poorly defined. And opening up pipe piles and H-beams are coming to that. And basically what happens is that soil goes places where and does things you really don't want it to do to alter the effective areas you're looking at. And that also relates to the issue of displacement as well. For example, closed section foundations tend to be displacement piles. Open section tend to be non-displacement piles. And tapered piles have their own challenge. Tapered piles basically, and Nordland's method spends a lot of time modeling tapered piles, such as wood piles. Basically, they interact with the soil and the pile interact along the shaft of the pile little differently than they do just a straight frictional. There's a little end bearing mixed in there. It can get complicated. Those are and of course I also mentioned the cavity expansion issue as well, but that's a whole different subject. Plugging is something which is only now in the last 10 or 20 years is really getting quantified the way it should. With an open-ended pipe pile, if you drive an open-ended pipe pile, then you have an issue of whether or not the plug in the middle of it is going to go down with it. And if it does, in other words, if the surface of that plug is at the toe of the pile, then you do not have plugging. If it doesn't go with it, then you do have plugging. And that, whether it does, depends on the type of soil. And then basically to estimate has been traditionally been done using a statics method of statics to figure out how deep the plug. The plugging can definitely affect the drivability of a pile, and severely in many cases. So plugging is an important issue. It's a complicated issue. The approach your book gives, and it gives a nice explanation of it, is something that you have to take into consideration when you're driving, particularly either open-ended pipe piles, open-ended pipe piles. Open-ended pipe pile plugging takes place at the toe. H-beam plugging, and I have a little shot in the corner of this slide which shows you what one of the people who used to work for me actually pulled a plug out from the side of an H-beam driven in the yard. H-beam plugging is a whole different phenomenon in a sense, in that it takes place along the shaft of the pile. And basically the way you deal with H-beam, if you assume you have H-beam plugged, let me just back up. If you can, I talked about when we were talking about, for example, this again, that the perimeter of the pile is all the way around this way. With an H-beam, the perimeter is in rough terms 6 times the basic flange width of the H, because with H-beams are set up so that the flange width and the depth are basically the same. And the wetted area is 6 times. If you get H-beam plugging, then basically what's happening is that between the tips of the flanges, in other words, if this is the H-beam, this is half the H-beam, this is the other half obviously, this is half the H-beam, and this is the plug inside. Basically what happened, as you see a little bit in that photo, is that it shears along between the two tips. And this area, and basically all this area here is no longer really available to you. So if you have reason to believe you're going to get H-beam plugging, you simply say that the wetted perimeter is not 6 times the size, but 4 times the size, basically along the flange, between the two tips, and on the bottom flange. 4 times, like a square pile. That's the difference between, that's the effect of H-beam plugging. It reduces your shaft resistance, your shaft capacity. Soil setup is another interesting topic. It's an important one. Basically, and there's a lot of literature on this subject, a lot of it. In fact, there's one researcher down in Alabama that's made a career out of this, and with good reason. Soil setup is an important thing to understand. If you are basically, there are 2 things that happen when you, and it's primarily in clay soils, and I'll explain why. With soil setup, what's going on is that if you drive particularly a displacement pile, like a concrete pile, so say we're driving a square concrete pile, 2 things are going on while you're driving this thing. One of them, in addition to whatever remolding you get of the clay, one of them is that you gain cavity expansion effects. The soil around the pile is compacting. You're displacing soil, and soil is compacting around the pile. At the same time, you're also, if it's under the water table, if you're dealing with soils under the water table, you're also displacing water. And you're basically forcing water out from where the pile was. So what happens is this. If you remember from consolidation, and you remember we've got a soft clay layer with lots of water in it, and you apply a load this way. And what happens is that the immediate effect is that the poor water would take the load. But the poor water, like again, I'd use my group dynamics issue, some of your members of a group, they decide that they just want to get out under the pressure. So what they do is the pool water heads for the exits, either one-way drainage going up, or two-way drainage going just up, or two-way drainage going both up and down, depending on what's on around it. And as that pool water leaves, it compacts. Well, what happens in a pile is basically a consolidation around the pile, where over time, after the pile is driven, the pool water will dissipate. Well, the pool water, because it's because of the way in which it's loaded, in other words, it's loaded in shear rather than, and as you know, and remember, for those of you who take me in fluid mechanics lab, remember, fluids that a true fluid is one that at static either deforms continually on shear or doesn't take the shear. Therefore, what happens is that we've got all this fluid that's been, the pressure of the fluid has been raised. That fluid pressure is pushing the particles apart because the fluid pressure has been raised. The fluid pressure between the pores acts on the particles and pushes them apart. And what that does, if you remember, is that it reduces the effective stress of the soil at the around the pile. Not because the water table is going up and down, but because the pool water pressure has temporarily been raised. And when that happens, your effective stress goes down, but that doesn't last forever. Eventually, those pool water pressures are going to dissipate. Things are going to get back to some kind of normal, and you're going to get capacity increase. In other words, as the effective stress around the pile will increase again as the pool water pressures drop, and when that happens, your pile capacity increases. This is referred to as setup. There are cases where and what will happen is that if you use some kind of driving criteria as a way of estimating, if you use some kind of driving criteria, you'll have to take that into consideration, because the piles will actually go in easier than their ultimate capacity, or whatever ultimate capacity you have without poor water pressure would indicate. If you don't take that into consideration, then you will basically unnecessarily degrade the axial capacity of the pile. Predicting setup is something of an art. Although I said we've made a lot of advances over the years, and you see these setup factors given here. If you're given that, if you need to, you can consult that table depending on the type of soil. Sands, some cases you actually get capacity goes down after it's been driven. Sometimes they'll do that because the particles rearrange, and basically their compaction decreases for particle rearrangement. But most of the time, sands, we don't worry about setup. Setup can be a very difficult thing to quantify, but it's important that we have some idea. I remember years ago, I was working on a project for the seismic rehabilitation of the San Mateo Hayward Bridge, and myself and some of the other engineers involved basically spec'd a much larger hammer. Spec'd a very large hydraulic impact hammer to drive. Some of them were 72 up to 144 inch caissons or cans or large pipes or whatever you want to call them, and they were basically driven into a template to support the bridge pier, so that in the event we had an earthquake, the bridge would be serviceable after the earthquake was finished. In other words, or to put it another way, to make sure the bridge wouldn't be finished after the earthquake was. But in any event, most of us involved, we're estimating very high, a lot bigger hammer. The hammer gets out there, the piles go in very easy. Now, of course, when you're dealing with those large of a project, you really don't want to show up with too small of a hammer. When you're, if you're down the lower ranges and the hammer is too small, you can get away with that. You just go bring a bigger hammer. But when you're in the upper ranges of hammer energy, there's not many of them around. You don't want to show up unprepared. So it was everybody's pleasant surprise. Well, why do we need this big of a hammer? Well, basically, most of us had assumed setup factors in the 2 range, when in fact, one geotech who had a lot of experience in the bay mud said that, well, setup factors there are 5. So that pretty much settled that, didn't it? So we could have used a smaller hammer, but then again, we did not. So setup can do some strange things to your, if you're not really careful. And that's another place where experience is important. Well, at this point, I'm going to stop my presentation on bearing capacity of piles, and we'll deal with settlement. We'll get to settlement and group effects the next time. So until then, thanks for watching, and God bless.